calls it B, as far as I can tell, and I just can't find it. Federico, where's the Cartan matrix on this? Where is that covered?
I can help you look it up. I can't remember right now. So we're ready for this classification of finite Coxeter groups. We're going to see what all the finite Coxeter groups are. We're going to prove that there aren't any other ones. Before I do this, I'm sorry that I got stuck at the consulate last Wednesday, so I'm going to have an office hour today from 2 to 3 to make up for that. So remember that the key thing we proved already is that the Coxeter group is finite if and only if the associated bilinear form is positive definite, which last time we developed a computational way of figuring out if bilinear form is positive definite. This is basically if the principal minors of this associated matrix minus cosine of pi over mij over I and j are positive. Okay. And so what we're going to do to classify these things is just figure out when these matrices are positive definite by doing this computation. So, let me start with a graph, gamma. So it looks like this. Who knows what it looks like? There's numbers, mij on the graph. They're positive integers or they're infinite. And we're making a matrix, a gamma out of this. And remember, the conditions are that mii is 2, mij is greater than or equal to 3, and it's equal to mji for I not equal to j. And we agreed that if there is no edge between two vertices, that means that mij is 2. So that means that this is a lie. Am I saying this correctly? No, I think MII is 1. And mij is greater than or equal to 2. Okay. And so the question is, when is this positive definite? So let me give you the answer, and then we'll prove the answer. So theorem. It's one of our main theorems in this course. The irreducible finite Coxeter groups are those corresponding to the following Coxeter diagrams. So we're going to give a complete list. So first of all, we know AN gives me a finite thing, gives me a finite Coxeter group. The group that it gives me is the symmetric group. We saw Bn It's the same diagram, but it has a 4 here. This gives me the hyperoctahedral group. Then Dn looks like this. Okay, so we haven't talked about this group before, but it turns out that this also gives me a finite Coxeter group. Okay, and basically these are the only 3 infinite families. Okay, so if you go to n very high, then the only 3 finite Coxeter groups you're going to see are this one, and this one. And then there's some kind of anomalies that occur for lower values of n, which look like this. So this one is called E6. Then E7 is the same thing with another vertex. E8 is the same thing with another vertex. So these guys also give me finite Coxeter groups. Okay. Then there's another one called F4, which looks like this. There's another one called H3. Looks like this. H4 looks like this. And I2 of M looks like this. And that's it. These are all the finite Coxeter groups. You should realize this is an amazing theorem. First of all, it wasn't even clear we were going to get a nice answer. Right? It could be that we define Coxeter groups in a very general way, and we're asking which the finite ones are, and that might have been a hopeless question, but it turns out that this is it. Okay? Now, as you'll realize, also the subscript refers to how many generators these things have. Right? So this thing is called E8 because it has 8 generators, and these certain relations that you read off from here, etc. Okay? So this is the theorem that we're going to prove today and next time. Okay? So how are we going to prove this? Well, what we're going to do is the following. First, I'm going to prove that these Coxeter groups are finite. All of them. We know that about AN and BN, and about I2 of M, that's the dihedral group, but we don't know the other ones. And so we have to prove that they're finite. And the way I'm going to do that is by proving that the principal minors are positives. Now, let me point something out to you. For example, let's say that I want to do this for E8. Okay, so looks like this. 1, 2, 3, 4, 5, 6, 7, 8. Now I need to make a matrix out of this, right? So how do I make a matrix? Well, the first thing I should decide is what, it's going to be an 8 by 8 matrix. Okay, the rows and columns are indexed by the generators, and so the first thing I should do is decide what order I'm going to put them in. Okay, and let me choose some random order. Okay, so I do it like this, and then here I insert minus cosine of pi over mij. So for example, for 1 and 2. Mij is 2, and so the number is 0. Also, we know along the diagonal, these things always have what do I want to do? I want to multiply this by 2, actually. We'll see in a second why. So instead of, of course, if I multiply this matrix by 2, then the determinants are going to be, whenever I compute a determinant like this, it's just going to be off by a factor of 2 to the something, right? For example, if I multiply the whole matrix by 2 and I compute the determinant of the whole matrix, then it's going to be 2 to the n times the older determinant. And so actually what I'm going to want to do is compute 2 A gamma, and the reason is that if I did just A gamma and I started computing these determinants, I would get powers of 2 everywhere. Okay? And so instead I'm just going to do 2 A gamma. Okay? And so in 2 A gamma, we're going to see always 2's along the diagonal. Okay? Because I get 2 times minus cosine of pi, which is cosine of pi is -1. So I guess what I'm really doing is minus 2 A gamma. Oh, yeah, sorry. 2 times minus 1 is 1. Times 2 is 2. Thank you. So 1, 2, I get a 0. 1, 3, I get a 0. 1, 4, I get a 0. You see, I get a lot of zeros. Well, first of all, I should have 8 things, right? So okay. But what's the point that I want to illustrate here? I mean, first of all, you get a lot of zeros, but some things are not 0. Okay, so and maybe it's good to remember this, that if you have no edge, you get a 0, and if we have an edge like this, what do we get? I get 2 times minus cosine of pi over 3, so that's minus 1. So whenever I have an edge like this with no label, I get a minus 1. So for example, let's do the row 1. So 1 and 1 is 1, 1 and 2 is 0, 1 and 3 is 0, 1 and 4 is 0, 1 and 5 is 0, 1 and 6 is -1, 1 and 7 is 0, and -1. Okay? And I know this thing is symmetric, so it's going to look like this also. And etc. Okay? But the point I want to make by doing this is the following. I need to take this and I need to compute all the principal minors. There's 8 of them, right? Now, let's look, for example, at the 7th minor. Okay. What am I doing if I consider just the 7th minor and I need to prove that that determinant is positive? Well, if I take the 7th minor, basically what I'm doing is I'm forgetting that the 8th generator exists. Okay. So what I'm going to get, if I forget about this, is I'm going to get to forget about this guy over here. Okay? And so the determinant of the 7th minor is equal to the determinant of this guy, this Lincoln diagram, this Coxeter diagram. Right? Because if you just forget about this, then the matrix that you get is exactly the matrix that you would get if you didn't have this guy here. Okay? So I would get the determinant. Let me just write it as a shorthand like this. Okay? So that's the first thing. Okay? But the second thing I'd like to illustrate to you is that actually, when you need to compute the determinant of the union of two graphs like this, what does this look like? Well, here's 1, 2, 5, 6, 3, 7, and 4. Okay? Now, so what does this matrix look like if I... So this is this same guy with this last row and last column missing. Okay? I need to compute this determinant. Now, let me switch the rows around. Okay? So let me do it like this. What's the effect of switching rows around when, for example, if you switch two rows, what happens to the determinant? You guys remember? If you switch two rows of a matrix, the determinant changes sign. Okay. Now, if I switch them like this, what I'm going to get is basically, I'm going to have to change signs a bunch of times, right? How many times do I have to change signs? Well, just however many transpositions it took me to get from here to here. Okay. So that happens when I switch the columns around, but now I want to do the same thing to the rows. Because I want to get the rows in this same order. Okay. Then I need to change the sign again, and I change it in exactly the same number of times, which means that because I changed the same thing in the rows and in the columns, I haven't changed the sign. Okay. So if I want to compute this determinant, okay, if I want to compute this determinant, is the same thing as this determinant. Okay. But why is this order preferable? Because you see, 1, 2, 3, 5, and 6 are connected to each other, and they're not connected to 4 and 7. Okay? Which means that if I look at this matrix like this, all the entries over here are between 1, 2, 3, 5, and 6, and 4 and 7, which means that this is 0 right here, this is 0 right here, and I need to compute the determinant of a matrix that looks like this. And one of the properties of determinants is that when you have a matrix of this form that has 2 square blocks and zeros here and zeros here, then you just compute the determinants individually and multiply them. So that means that all I have to do is compute this determinant and multiply it by this determinant and prove that that's positive. Okay? But if you look at this, this is the diagram of the 5. And this is the diagram of A2. So what am I saying? I'm saying when I need to check the 7th minor of E8, that computation is reduced to just the full matrix for D5 and the full matrix for A2. And this is going to happen every single time. If you look at computing a minor of one of these matrices, what you end up computing is the determinant of some subgraph of this graph. Okay? Or maybe a product of them. And then you can say, well, okay, well, inductively, let's say that I already did it for all the smaller graphs, so I'm going to get that this was already positive, this was already positive, and therefore this minor is positive. A key property is that if you look at this list, then if you look at any subgraph of anything in here, it's also on the list, or the connected components. Yeah? For example, I did it over there. I took E8, I took a subgraph, and that split up into 2 smaller things on this list, D5 and E2. And if you look at this diagram carefully, and you'll see that no matter what subgraph you take, the connected pieces are also in this list, and they're smaller, which means that by induction, I don't have to check the smaller principal minors. All I have to check is the main matrix. Okay. So by this argument, it's enough to check that the determinant of A gamma is positive for all of these guys. So the full determinant. And then the smaller principal minors are going to follow from that. Okay. And so what we're going to do now is compute the determinant for each one of these things. So let me remind ourselves that no edge means you have an entry of 0 in A gamma. An edge like this looks like a 1, minus 1. And an edge like this looks like minus 2 cosine of pi over n. And in the diagonal, we always get 2's. So for example, we need to compute the determinant for, let me call this quantity d of gamma. Okay? D of a diagram is going to be the determinant of its matrix. So for example, what's d of an? Well, d of an is going to look like this. We have n generators, 1, 2, up to n. And what does this matrix look like? Well, first of all, we know that it has 2's on the diagonal. Okay? Now, what edges do I have? Well, I have an edge between I and I plus 1, which means that I should put a negative 1 in those positions. So I should put a negative 1 here, and here, etc., up to here. And this thing is symmetric. I better put them on the other side also. And what about the other edges? The other edges are not there, so it's just 0 here and 0 here. And so we're left with computing a determinant like this. Okay. Now, how do you compute a determinant like this? And here I actually need to ask you guys, because, and I should explain to the class in Colombia that the linear algebra course that is done here is very much determinant. And I want to make sure that you know what to do if I'm actually asking you to compute this determinant. So do you know what to do? Okay. Well, so here's how you compute. I mean, there's different ways of computing determinants. One thing you can do, well, let me just show you the way we're going to do it. The way we're going to do it is by this thing where what you do is that you expand by cofactors in a recursive way. Okay. So, for example, how does this work if I want to compute the determinant of something like this? That means that I choose a row or a column. And you would like to choose it so that there's a lot of zeros on that row or on that column. And I should tell you that this expansion by cofactors is especially well suited for when you have a lot of zeros in your matrix. So let's choose this guy. Okay. And then what you do is that you say, okay, let me take the first entry and I have to multiply that by the determinant of the matrix, which I obtained by removing that row and that column. Okay. So I remove this row, I remove this column, and I get this smaller determinant. What does it look like? It looks like this also, except that it has size n-1. Then I go to the next entry. And I do the same thing. So -1 times what you obtain when you remove this row and this column. So what does this thing look like? It looks to me like we're going to get a single -1 in here. And then we're going to get a -1, zeros. It's going to look like this. Then I go to the next one. It's a 0. So 0 times whatever you get, but you're going to multiply it, so it doesn't matter. And then the next one is a 0, etc. And what you do is that you take the alternating sum of these things. This is how this expansion works. So you take this minus this plus this minus this, etc. So this is the way of expanding a determinant. Compute a determinant by cofactors. Okay. So what's this thing? Well, you see, this is exactly the same matrix, except that now not for an, but for an minus 1. So I get 2 times the matrix for an minus 1. And then minus minus 1 is plus 1. And now I need to compute the determinant of this thing. So how do I compute the determinant of this thing? Do I recognize it as one of those? Well, this is not exactly a matrix of a graph because it doesn't have 2's on the diagonal. So I have to figure out some way of computing this. How do I do it? Well, I use cofactors again. So I choose a row or a column that has a lot of zeros. And you see there's a very good choice. Because this column is basically all zeros except for one entry. And so when I apply this cofactor expansion, I'm going to get a single term, which is minus 1 times the determinant of this matrix. And this is one I recognize. Okay? It's the same matrix, except that now what size does it have? N minus 2, because it has size n, then I chopped off one row and column, and then another one. Okay? And so what I get is 2d of a n minus 1 minus d of a n minus 2. Okay? So I didn't get the answer, but this is good because I got a recursion that tells me if I know these two, I know this one. And that means all I have to do is just compute the first, A1 and A2, and then I'll get all of them. Okay? So let's go ahead and do that. So what's the determinant of the graph of A1? Well, what does my matrix look like in that case? It looks like a 1-by-1 matrix that has just a 2. And the determinant of this thing is 2. Right? What does d of A2 look like? Well, it's the determinant of, I have 2's here, and I have minus 1 here. And so that's 4 minus 1, 3. And given these two values, I can start computing. So what's d of A3? It's 2 times this minus this. So 2 times 3 minus 2 is 4. D of A4 is 2 times 4 minus 3 is 5. You see the pattern. Right? 2 times 5 minus 4, 6. Okay. And then you see that what we have proved by induction is that d of an is n plus 1. And that's a good answer because we wanted to get a positive answer. Okay. So that's good. And, well, what did I prove? What I proved is that this thing is a finite Coxeter group, which you shouldn't be too impressed by because we knew that already, right? This gives me the symmetric group. Okay. But what you should be impressed by is that we did it in this way that is actually going to allow us to do it for all the other ones. Okay? So this thing has determinant n plus 1. Okay? Now, how do I imitate this computation so that I can apply it to all of these things? Well, let me look carefully at what we did, and we'll see that actually there's very little that you have to change to make this work. Because what if this is not exactly the same? If it's not exactly an, but it's any one of these diagrams, okay? And I want to imitate the same computation. So I would like to choose a row that has very few non-zero entries. Now, every row has a 2. Okay? And every row is going to have at least another entry because every vertex is connected to something else. Okay? The reason that this guy only had 2 entries is that in the diagram of an, the first vertex is only connected to one other vertex. So that's why we only had 2 entries here. And we would like to do that for the other diagrams. And you see that in all of the other diagrams, we can also find a vertex that is only connected to another vertex. So in general, this is not going to look exactly like this, but it's going to look very similar. Because I can choose my labeling. In such a way that, so now this is for an arbitrary graph gamma on this list. Okay. Well, I choose my labeling so that gamma looks like this. Here's vertex 1, and then here's vertex 2, and then I don't know what happens after that. So the only thing I'm assuming is that vertex 1 is only connected to vertex 2. Okay. 2 might be connected to several other ones, I don't know. And then here, who knows what happens. Okay. If my graph looks like this, then what does the matrix look like? Well, the first row has a 2 here. What do I have here? Well, it depends on the value of this edge, right? So I don't know. Let's say that this edge has value m. Then I need to put minus 2 cosine of pi over m here. But the rest is zeros. And the same thing here, minus 2 cosine of pi over m. 2, the rest is zeros. And for the rest of the matrix, actually, I don't really know, right? There might be, 2 could be connected to a lot of things, so I don't really know what's going on for the rest of the matrix. But I know that this part looks like this. Okay. And then I know, of course, that the diagonal is 2's, but I might not know a lot more. But you see, I can make exactly the same expansion by cofactors. Except the only thing I have to change is that I get 2 and then minus. So I get 2 times this matrix. Okay. Now, what is this matrix right here if I remove the first row and the first column? Well, you see, just like in the previous case, if I remove the first row and the first column, it's as if I had removed the first vertex. And what I get is just the determinant coming from this graph. Okay. And so what I get is the determinant of gamma minus the vertex 1. Okay. Maybe just to make sure that you understand, let me just call this gamma prime, where gamma prime is this graph. Okay. Minus the next term is minus 2 cosine pi over m and something like this. Okay. Now what does this look like? Minus 2 cosine pi over m, and the determinant that I get is going to look like this. I lose this and I lose this. So the first column is minus 2 cosine pi over m and zeros. Okay. Now, what I get then is this matrix, which I don't really know much about. So here, there's just some things. Okay. What things? Exactly these things. So this piece right here is the same thing as this piece right here, right? Because I'm erasing this column and this row. So I don't really know what it is, but I know that it's whatever is here. Okay. So again, the nice thing about this is that by induction, I'm already going to know what this term is, okay? Because this is a smaller graph. And now I'm left with computing this second term. But you see the same thing happens as in the previous case. Well, minus and minus gives me a plus. And now I need to compute this determinant, but then I, again, expand by cofactors on the first column, and I get that the only thing that survives is minus 2 cosine of pi over m times the determinant of this matrix with this thing eliminated. Okay. So let me times the determinant of this guy with the top row removed. Okay. Now, so I get 2 times d of a gamma prime minus 4 cosine squared of pi over m. And I just need to figure out what this determinant is. But what is it? Well, if we look at it, it's whatever goes here. Right? This is the determinant that we're computing now. How do you get it? You get it by removing the first 2 columns and the first 2 rows. And so what we get is exactly the graph that you would get if you remove 1 and 2. Okay? And so this thing right here is the value of d of a gamma double prime, where gamma double prime is obtained from this guy by further removing vertex 2. Okay? And then recursively, I'm going to know what these 2 guys are, and I'm going to get the value. Okay? So that's my plan. And so this is my little lemma that I wanted to prove. So it looks like this. Okay. And now I just compute. Okay. So So let's do it, for example, for, I don't know, what's interesting. Let's do it for dn. So let's apply this to dn. Okay? So let me label dn like this. 1, 2, n minus 2, n minus 1. So what happens when I apply this formula? Well, again, all I have to do is take 2 times d of what I get when I chop off the first guy. So if I cover this up, what diagram do I get? Well, I get exactly d n minus 1. Okay. And then I get minus 4 cosine squared of pi over m, which, remember, when m is equal to 3, like it is in this case, then cosine of pi over 3 is a half. And so we just get minus d of the graph you obtain when you remove 1 and 2. So what does that look like? Well, it's dn minus 2. So you see I get exactly the same recursion that I got for an. But to be sure that these things are positive, I have to compute the first values. Okay. So, for example, what's the first d, by the way? What's the smallest that I need to compute to make this work? Well, the idea of dn is that it has a branching point. And so, in order for this in order for this dn not to fall as an an, then n has to be greater than or equal to 4. So in other words, I should be computing d4 and d5. Okay. So what's D4? Well, I do the same thing. 1, 2, 3, 4, right? So it's equal to 2 times removing 1. What do I get? This is the diagram for A3. Minus removing 1 and 2. What do I get? I get something that looks like this, which is just the diagram of A1 twice. And we said that when you have two components, you just multiply. So this is 2 times d of A3 minus d of A1, d of A1. Okay. So d of A3 is 4, so we get 8. D of A1 is 2, so we get 4. And so this is 4, which is fortunately positive. Okay. We do this for D5. Okay. So we get rid of the first vertex, and we get D4. We get rid of the first two vertices, we get A3. And so what we get is D of 2 times 4 is 8, minus d of A3 is 4, so we get 4. So d of D4 is 4, d of D5 is 4, d of D6 is 2 times 4 minus 4, 4, etc. By induction, it follows that d of Dn is 4. Positive. So that's good. So we keep doing this, right? We keep doing this. For example, for Bn, what's going to happen? We get again exactly the same recurrence, right? It's just that the initial values are going to change because B2 is different from A2 and B3 is different from A3. So, by the way, when does Bn? When should we have a Bn here? Well, basically, if we have only two vertices, then it's actually one of these guys. And so this really makes sense for n bigger than or equal to 3. I mean, it's different from this for bigger than or equal to 3. An is for any n. Okay. Okay, so that's how you do these guys. Now, I don't know. How do you do E8? I mean, you keep doing the same thing. So how do you do E6? Well, we just pick this to be the 1, remove it, and we get D5. Remove both of them, and we get A4. And you just figure out what that number is. Okay. And, so we know that this is always 4. And if you compute E6, you're going to find that it's 3. If you compute Bn, you're going to find that it's always 2. If you compute E7, you're going to find that it's 2. If you compute E8, you're going to find that it's 1. And that tells you why there's no E9 here. Because if you compute it for E9, which is for adding another vertex, then you get a 0. And that means that that would not be positive definite, which would mean that that's not a finite Coxeter group. So that's why this is kind of an anomaly that stops at dimension 8. Okay. Does anything strange happen here? Not really. You just go ahead and compute this, and you find that it's a 1. You compute this. Here, it gets a little bit messier. Why? Because you see, at some point, you're going to have these cosines, right? And here, you have a 5, which means you're stuck with a cosine of pi over 5. Okay? There's nothing you can do about it. And so that means that when you compute this, you have to figure out what cosine of pi over 5 is. And you can do it. It'll take you a little while, but you find that this is 3 minus square root of 5. Okay? You have to think for a second, and so that is positive. You compute this, 7 minus 3 square root of 5 over 2. And again, it takes you a second to realize that that is positive. Let's do I2 of m. So D of I2 of M. Well, it's a 2 by 2 matrix. It has 2's on the diagonal. And here we have minus 2 cosine of pi over M, minus 2 cosine of pi over M. The reason I want to do it is because it's an infinite family. So 2 times 2 is 4, minus 4 cosine squared of pi over M. And this is 4 sine squared of pi over M. And luckily, it's positive. I mean, it's not lucky. We should expect this to be positive because we know that this is the dihedral group, which is finite. Why is it positive and not 0? Because it would be 0 only if you were plugging sine of 0. But this is pi over M. Or, pi over 1 would also give 0, but M is greater than or equal to 3. No, okay. Anyway, so that proves that these guys are finite. Okay? And so that's a start. We know that all of these Coxeter groups are finite. And what we're going to do next is prove that if you are a finite Coxeter group, then you must be on this list. You can't be anybody else. So let me start that argument. So this was first one, step 1 was to prove that these guys are finite, and step 2, if W is finite and irreducible, it's on this list. Okay? And the way we're going to do this is I'm going to start with some graph. So suppose gamma gives me a gamma positive definite. Okay? And through a series of reductions, I'm going to conclude that gamma must be on this list. Okay? So what's the first reduction that I want to make? You see, I never see any infinite in any of these graphs. And I want to show that there's a reason for that. So this guy cannot have an infinite edge. Why is that? Suppose that it did. So suppose gamma looks like this and it has an infinite edge. It's supposed to indicate that this is a finite group. Okay. Now, what happens when I just look at these two vertices? Well, these are two generators, right? I look at the subgroup generated by them, and so this is the parabolic subgroup. It has this diagram. Okay. Now, my big group is supposed to be finite, which means that any subgroup of it should be finite. But this is the infinite dihedral group. This is the infinity, which is not finite, which means that the big group can't be finite also. Okay. So that's the first reduction. Okay. And well, maybe I won't rush through this. So the next time, well, I mean, now we know that gamma can't have any infinite edges. The next thing, just to give you an idea, the next thing I will prove is that gamma can't have cycles. And you see that none of these things have cycles. So the next thing I would like to show is that if you have a cycle, then that forces you to be infinite. Okay? So that just to give you an idea, and that means then we're just going to be dealing with trees. And then I'm going to keep reducing the trees until I show that these are the only possibilities. Okay? Stop there. Sean do? Does he give it to you?
Yeah, we got the
Okay, there you go. I do. What? What's up?
I need to know which quiz that was. At an hour after class. No, you Why do you need to know? I'm curious. Professor Lee. Did he tell you?